Okay, so this is the Physics Lab 1 constant velocity. So in this lab, we investigated how an object moves when it travels at constant velocity. So the purpose and goal was to analyze motion using both experimental data and computational model, and then comparing the two. So to do this, we rolled a roll of string across a flat table and recorded its motion using video tracking software, and then from that video, we measured position over time to determine how the object moved. And then we built a computational model using physical equations to predict the motion and compared those predictions to what we actually observed. And that helped us better understand Newton's laws, especially how motion behaves when the net force on an object is close to zero. So for the fundamental principles and models, after the initial push, the roll of string experienced ultimately no net force, so its acceleration became approximately zero. And according to Newton's second law, if the net force is zero, that means acceleration must also be zero. And so when acceleration is zero, velocity stays constant, which is exactly what we observed in this experiment. And because velocity remained constant, the position increased steadily over time, which is why the position versus time graphs appear nearly linear, which we will see later. And these relationships were used to build our computational model to predict motion. So for the code, this is the computational code used to model the motion of the roll of string. And in the code, we first define the system properties and initial conditions like object's mass, radius, initial position, and initial velocity. And then we also set time step, which controls how often the program updates motion calculations. And then the program then enters a calculation loop where it repeatedly updates velocity and position over small time intervals. And then using Newton's second law, the program calculates acceleration based on net force. And since the net force after the push is around zero, acceleration is also close to zero, so velocity remains nearly constant. And the code continuously updates the object's position using this velocity to store the values so we can later make the graphs of the position and velocity over time. So these predicted results from the model are then compared with the experimental data to see how well the physics model matches real motion. So this slide shows the experiment setup and a short video clip of the roll of string moving across the table. So yeah, the system being studied is the roll of string itself, which has a mass of 0.25 kilograms and a radius of about 0.045 meters. And the surroundings include everything interacting with the roll, mainly the table surface and the area around it. So in the video, the roll is first pushed, and then there applies a force and starts the motion. So after the push stops, there's very little force acting on it, so then the net force becomes close to zero. And because the net force is near zero, acceleration is also close to zero. And that means velocity will stay constant, and that is why the roll continues moving steadily across the table. So then this motion was recorded and later analyzed using the tracker software to measure position over time. So this is the data from observed experimental versus predicted data from the computational model. So the table shows position values measured from videos at different times, while the predicted column shows the values calculated by our model. And then the graph makes this comparison easier to see, where blue lines represent the observed motion and then the red line represents the predicted. So both lines decrease almost linearly over time, which indicates that the object moved with nearly constant velocity, and that matches Newton's first law, since after the push, the net force on the roll was close to zero, so acceleration was nearly zero. And then the predicted and observed lines are also very close, so that means that the model successfully represents the motion, but they're not perfectly identical just because of real-world effects, which we'll talk about in later slides, like friction, measurement uncertainty. So overall, this comparison shows that the computational model gives a good approximation of the real motion observed in the experiment. So these are the analysis and possible errors that come with. So in our computational model, we assume motion occurred in one dimension, friction was small, and the net force after the push was around zero, so that velocity would remain constant. And the tracker data supported this assumption because position changed almost linearly with time and acceleration remained close to zero, meaning that constant velocity motion. And the predicted results from the model and the experimental data showed very similar trends, although they were not perfectly identical. So this does confirm Newton's first law, since the roll of string continued moving steadily when the net force acting on it was approximately zero. So differences between a prediction and observation are mainly just due to external factors, and those possible sources of error would be small unintended forces like during the push that happened, friction between the roll and the table, tracker measurement inaccuracies, and camera angle distortion. So these factors cause small deviations between the ideal model and the real motion observed. So on what-if scenarios, consider what would happen if the axes in the tracker software were flipped, and in that case, the direction of motion would change sign, but the magnitude of velocity would remain the same. So the graph would simply slope in the opposite direction. And overall, this experiment demonstrates how this demonstrates constant velocity motion and supports Newton's first law, which states that an object continues moving at constant velocity when no net force acts on it. However, in real situations, it is difficult to achieve perfectly zero net force just because of outside factors like friction and air resistance that are always present. So this is why there are small differences between predicted and observed motion. So even though our model assumes ideal conditions, the experimental results closely follow the predicted notion, showing that the physics model gives a good approximation of real motion. And thus, therefore, this experiment shows how experimental data and computational modeling can be used together to understand how objects move when forces acting on them are minimal, while also incorporating and proving Newton's first and second law.